The objective of this lesson is to find the inverse of exponential functions, which will result in logarithms. So we will introduce the idea of a logarithm as the inverse of an exponential, and we'll actually do the work to find the inverse of the exponential. So our steps for this process are, first of all, to swap the x and the y. And then once we've done that, when we solve for y, we're going to do that by using logarithms. So our first example here, we'll set up, first of all, as y equals 2 to the x. We'll swap the x and the y, so that becomes x equals 2 to the y. Now, in order to get that y out of the exponent, I'm going to rewrite it as 2 to the y equals x, and then go log base 2 of x is equal to the y. So notice that the y is now out of the exponent. Logarithms help us get those variables out of the exponent. So there's our inverse function. The inverse of x is equal to log base 2 of x. Let's take a look at number 2. For number 2, we're going to go ahead and set it up as y equals 10 to the x plus 7. We'll swap the x and the y for the inverse. So we have x equals 10 to the y plus 7. And then we're going to go ahead and get rid of the 7 by subtracting it from both sides. Now I prefer writing the exponential on the left side, so 10 to the y equals x minus 7. And then we can circle through here and say we're going to have log base 10 of x minus 7. I'll put that in parentheses because that whole thing is inside the logarithm. So to represent that, we'll put it in parentheses, and then equals y. Now, the next step is to, when we do this, notice that log base 10 is our common log, so we can rewrite this as y equals just log. We don't need the base 10, just write it as log. So our inverse function for h is log base 10, just common log of x minus 7. So the reason why we do this now is because for the next problem, we're going to have several more steps to this. And so if we do each step piece by piece, it should lead us to our final answer. So on this one, we'll go ahead and start off with writing it as y equals. So y equals 1/4 times 3 to the x plus 9 power minus 6. Then the next step is to go ahead and swap the x and the y. Now look how embedded this y is on the right side. That y is in several layers of the function before we can get to it. So the first step we'll do is we'll add 6 to both sides. So x plus 6 equals 1/4 times 3 to the y plus 9. And the next step to get rid of that 1/4 is I'll multiply both sides by 4. And when I do that, I'm not actually going to distribute it through. You can, if you would like to, distribute it through, but we oftentimes will leave it in factored form with that common factor out to have the x by itself, because if we were graphing, this would help us find the asymptote. It's easier to say that the asymptote would be x equals -6 in this form, rather than having to set 4x plus 4x plus 24, because you got to distribute through the 4 to both spots, set that equal to 0 and solve. All right, next step, we want to get the variable out of the exponent. So we'll rewrite it on the left side. And then I'll go ahead and take the log, and then I have log base 3 of the 4 times x plus 6. It might be helpful to put the whole thing in brackets to show that we have the whole thing inside of the log, and that's going to equal the exponent y plus 9. Now we still have that extra step of subtracting 9 from both sides, so log base 3 of 4 times x plus 6 is going to equal, minus the 9 is going to equal my y, so my inverse function for g inverse will equal log base 3 of the quantity 4 times x plus 6, that quantity, minus 9. So when we're doing inverses, it follows some of the same rules as finding inverses in the other problems we've done. You're still going to swap the x and the y and solve for y. But in the process of doing that, you might have to use several extra steps as well as converting at some point from the exponential to the log, because our main idea is that the inverse of an exponential is a log.